clouds of gas and dust, the nebulae, made luminous by the radiation of stars within or near them, or darkly obscuring the light of whatever lies behind them. Here, new stars are being born. About a half-century ago, our galaxy was thought to be alone in the universe. We now know it to be one of a local group of about 20 galaxies. And strewn through the vast reaches of space are more than 10 billion galaxies grouped in clusters as far as our most sensitive instruments can reach.
The stars and galaxies tantalize us with their faint light. They're incredibly far away. Well, how can we hope to learn anything about something so remote? All we have is their light, and there's precious little of that. But we can make a handful of careful and subtle measurements of that light, and so then learn something about the universe beyond the solar system. And the most fundamental thing I suppose we could measure, one of the most important things, is simply just the position of that star or galaxy, the source of the light, where it is in the sky. And the next most obvious thing we might measure is any change that occurs in that position. The change is just an indication of its motion. And actually, the most obvious motion, and one of the most important motions we detect, is not really due to the distant star at all. It's due to us, really the Earth, because the Earth is moving in its orbit around the Sun. And so that changes our vantage or viewpoint of the stars beyond our solar system, and so makes them appear to shift position compared to other things even farther beyond them. Well, this is an effect of parallax, and it's very easy to see how it works. All you have to do is just close one eye and hold your thumb out at arm's length and cover up my smiling face on the television screen. Now, you should be stepped back from the screen, oh, say 6 or 7 feet. You shouldn't be too close to the television anyway. And then when you're back that distance and you've got one eye closed and your thumb covering up my face on the screen, well, of course, you look pretty silly, but that's okay. Don't worry about it. Nobody can see you. Okay, now, close the eye that is open and open the eye that is closed. And as you do that back and forth several times, what you'll see is that your thumb shifts its position compared to the image on the screen. Now, that occurs simply because you're shifting your point of view from one eye to the other over a baseline, which is just the distance between your two eyes. Well, that's the effect of parallax, of course, and we can use that to measure distance. You can see how this works by putting your thumb out again at arm's length and covering up the image again, but now pull it in twice as close and go through the blinking one more time. Now, if you do this, what you'll see is that the same shift occurs, but this time it's twice as great because the thumb is twice as close. Well, distance then determines the amount of parallax we measure, the amount of shift. That's a very important principle. Surveyors use that principle to measure distances on the Earth. They will measure the distance to some object far away from first one point and then another point. And the distance between those 2 points is again their baseline. Well, by the angles that they need and measure to the object that they're looking at, and by the distance along the baseline, they can triangulate the actual distance to that object, whatever it might be, and so map the surface of the Earth. We can map the universe in the same way. We use, for a baseline, just the Earth's orbit. The Earth, with its motion around the Sun, carries us to opposite sides of the orbit every 6 months. And so, from one side of the orbit to the other, we see the stars shift, because we've moved a distance on the baseline of 2 astronomical units, or nearly 200 million miles. And that then permits us to measure parallaxes for at least the nearest of the stars. But even the nearest of the stars have parallaxes that are extremely small, less, in fact, than 1 second of arc, or, that is, less than 1/3600th of a degree. Now, this is so small that the Greeks simply couldn't measure parallaxes, even though they knew that it was something that they might look for. They just didn't have the instruments to make the measurements. Well, this led the Greeks to some interesting conclusions. Because they couldn't find parallaxes in the stars, they concluded that the Earth must not move. For if the Earth moved, they'd see the parallaxes, and they didn't see them. Therefore, the Earth doesn't move. The Greeks couldn't imagine that the stars were so distant that the nearest of them, the very nearest, with the largest parallaxes, would still have parallaxes so small that they would be no larger than the size of this dime as you would see it from a distance of 1 mile away.
Once it was realized that the Earth goes around the sun, it was realized that we should be observing parallaxes of stars, an apparent change in their directions due to our changing vantage point as we move in our orbit. And from early times, astronomers had searched for parallaxes of stars, for trying to find ways of measuring that apparent shift. The actual discovery of stellar parallaxes was not accomplished until the last century, 1838, and in that same year, by coincidence, 3 astronomers measured parallaxes of 3 different stars independently. Friedrich Bessel in Germany discovered the parallax of the star 61 Cygni. Thomas Henderson in the Cape of Good Hope measured the parallax of the nearest star, Alpha Centauri. And Friedrich Struve in Russia measured the parallax of Vega. Modern measurements of the parallaxes of stars are carried out at special observatories with special kinds of telescopes. For example, at the U.S. Naval Observatory. The measurements are difficult and require the state-of-the-art to measure these extremely small angles. And even so, only the nearest stars are close enough that we can detect those very slight shifts. Stars farther away than about 20 parsecs, which is about 60 light years, are already so far that the errors of measurement are more than 10% of the angle we're trying to measure. So although parallaxes have actually been measured for many thousands of stars, there are only about 1,000 stars near enough that those parallaxes are accurate to even 10%. Consider, in the solar system, we know the distances to planets to better than 1 part in a million. We know the distance to maybe the nearest star to percent or a few percent. But even our comparatively nearby neighbors within 60 light years, most of them were uncertain by 10% or more.
The distance to even the nearest of the stars is truly staggering. Alpha Centauri is the nearest star, and it's actually a triple star system, 3 stars bound to each other by gravity. And this nearest of the stars is still 4 1/3 light years away from Earth. Well, a light year is just the distance that light travels in the course of 1 year, and light travels at 186,000 miles a second. Well, even at that considerable speed, it takes light from Alpha Centauri a little over 4 years to reach us here on the Earth. And if we don't care to wait for the light from Alpha Centauri to reach us, we might choose to travel there instead, across the 25 trillion miles of space. And if we were to go at, say, the same speed as an Apollo spacecraft, the vehicle that carried astronauts to the moon, still it would take us 1 million years to complete the journey. Well, we get the distance to the nearest of the stars with parallax. This is just a motion of the stars, but it's really a motion produced by the Earth. The stars themselves don't have a motion that allows us to get their distance, at least that directly. But the stars do move, and we can detect their own individual motions. They have direction and speed as they move around the galaxy in their orbits, and these combine to produce what's called the proper motion of a star. Now, the proper motion is just another shift in its position, but it's a very small shift because it depends on the distance to a star. And the star's distances, of course, are very great, so proper motion is really very subtle. You have to wait a long time for enough of it to build up so that we can measure it. Astronomers have to wait several decades, really, to get accurate measurements of proper motion. But they do wait those lengths of time. They are able to get them. But you have to really wait a much longer time in order to see real changes occur in the sky. The constellations that we view in our nighttime sky, like the Big Dipper, look today very much as they did in the past, say back 2,500 years ago in the time of the Greeks. They even look the same as they did to the Egyptians 5,000 years ago. We'd really have to wait much longer, say 100,000 years, before we in the future would see any really remarkable changes in the appearance of something like the Big Dipper. Well, proper motion tells us where the stars have been and where they're going. And like parallax, it leads to some extremely important information.
As early as 1718, the astronomer Edmund Halley had noticed that some of the stars had changed their position slightly compared to the positions that were shown for them on charts made by ancient observers. And this led astronomers to realize that the so-called fixed stars are not really quite fixed at all, but really do move, simply that they're too far away for us to detect those motions over a short time. By the time of Herschel, near the end of the 18th century, proper motions had actually been measured for a number of stars. Herschel used 14 of those proper motions to derive how the sun was moving with respect to its neighboring stars. The sun is approaching a direction in the sky that we call the solar apex. And of course, if you imagine yourself moving in a crowd milling around at random, as you go forward, people seem to kind of drift back behind you. And similarly, we can see the nearby stars apparently drifting backward as we move in our path through space. Today, we measure proper motions by photographing the sky with special telescopes several years apart. That is, we take two photographs of the same region with the same telescope several years apart, and then make careful measurements with microscopes on those photographic plates to detect the motions of the relatively nearby stars compared to the most remote stars, or better yet, distant galaxies.
One such special telescope designed to measure the motions of stars is the 20-inch astrograph at the Lick Observatory. During the period just after World War II, the sky was photographed with that 20-inch astrograph. Today, a second series of photographs are being made some 30 years later. The two plates of the same region of the sky are then compared in a special microscope to measure the shifts in position of the nearby stars, indicating that they have been moving slowly. If we were to follow the motion of a star, we would find that it moves toward or away from us, in this case, away from us, along our line of sight, and in addition, it moves across our line of sight. We measure the two components of motion with different instruments and with different techniques. This astronomer is measuring the angular motion across the line of sight of the faint members of a nearby cluster, the Hyades cluster, a family of a few thousand stars moving together through the galaxy. This cluster of stars was photographed a number of times in the 1940s with the 20-inch astrograph. Recently, the cluster was photographed again with the same telescope. The new plates are compared to the old plates on the field survey machine. A star that is a member of the cluster jumps back and forth in the same direction and by the same amount as do other members of the cluster. In the background, there are stars that don't seem to jump or have any measurable motion. They are so distant that it would take a much longer time between photographs, perhaps centuries, to detect any motion they may have. Thus, motion studies across the line of sight are at present limited to relatively nearby stars, but not so for line of sight motion, which can be determined as accurately for the very distant stars as for the nearby stars, provided there is sufficient light to make the required observation. We make use of a phenomenon of physics called the Doppler effect. This is a familiar effect on sound waves due to the motion of the sound source. For example, when a train passes with its whistle blowing, the sound of the whistle changes from a high-pitched sound as the train approaches to a lower-pitched sound as the train recedes. There is a similar effect on light waves from stars, a similar shift in wavelengths or colors. By measuring the extent of this Doppler shift in the light of a star with a device called a spectrograph, astronomers can learn how quickly a star is approaching the Earth or receding from it.
Well, by combining our measurements of a star's movement in the line of sight, so-called radial velocity, with its movement across the line of sight, a speed that we can determine by measuring its proper motion and its distance, we then can deduce its true space velocity, where it's moving, in what direction, and how fast. Now, as we gather all of these space velocities, these true velocities of stars around us, not only do we get an understanding about the general flow of stars around the center of the galaxy in the neighborhood of the sun, we have something available to us of potentially even greater significance. careful observations of the small little changes in the movements of the stars may be indications of the presence of invisible companions that may yet turn out to be the first planets discovered beyond our solar system.
Newton said if any particle which is isolated in space, it can be a star, moves in a straight line unless it's perturbed by another object, nearby object. So if we study the motions of visual stars, visible stars, the ones we can see, over a long period of time, perhaps we can detect that they are not moving in a straight line. Here we have a model. Here are two stars. They're a double star system. And one revolves around the other, or you can say they each revolve around the common center of mass. So as they go down through space, they're revolving around each other, and it's the center of mass that moves in a straight line.
I see.
Now, these are two visible stars, but what if we have one which is planet-like or so faint that it can't be seen, and then we observe the bright star by itself? But what is it doing? It's revolving around the center of mass, and and something else. And the easiest explanation is there's something out here perturbing, although we can't see it.
But
maybe a planet, maybe a small star.
At the same time, it's moving through space.
That's
with
right.
Proper
It's
motion.
moving through space. So instead of moving in a straight line through space, it moves in a wobbly line. But the wobble is very small.
Dr. Peter Van de Kamp of the Sproul Observatory, assisted by Dr. Lippincott, spent some 25 years studying the motion of Barnard's star, the second nearest star to the solar system after Alpha Centauri, and the star which exhibits the greatest proper motion. Their goal was to see if an invisible companion might be present which would cause Barnard's star to wobble around a center of mass and thus not follow a perfectly linear movement through space. Van de Kamp believes that he has detected such a wobble and feels that he has a strong case for the existence of one or more companions, perhaps a planetary system around Barnard's star.
The smallest unseen companion that we think we've discovered is the companion to Barnett's star. And that has a very, very small amplitude wobble. But we have over 1,000 nights of observations on this star, more than any other observatory. I wish other observatories had as many as we do, because over the years we believe that there's a wobble with a period of a little over 11 years, which indicate that this star is not alone, and it has a very small mass companion, perhaps of the order of Jupiter. We don't feel there's any reason in the world why we should be unique, that is the solar system. Why aren't there many more solar systems out in the universe? We do know there are lots of stars that are doubles. We see that there are two stars close enough together so that they revolve around each other as the planets revolve around the sun in our own solar system. So why not have many solar systems?
Not all astronomers are convinced that Peter Van de Kamp's measurements and interpretation of the movements of Barnard's star are real. Measurement of these small variations in proper motion are very difficult to make. The effects are extremely subtle. It's almost equivalent to watching a snail from a distance of about 100 miles away from it and observing it as it moves across your line of sight about 1 inch and does it over the course of, say, a decade or so. Obviously, that's very hard to measure. Well, in fact, the problem's even more complicated because the background stars that we use as our references also move, and their motions add errors into our measurements. Furthermore, even our telescope's own sagging under its weight will add additional errors still. And all of these things must be estimated and taken out if we're going to come up with the right answers. Well, it would be nice to have a more sensitive technique, something that would allow us to search for invisible companions in even more distant stars, let alone the nearby ones. And Dr. Donald Hall at the Kitt Peak National Observatory believes he has devised just such a system in the Fourier Transform Spectrometer, or the FTS.
A unique advantage of the FTS is its ability to measure radial velocities, or velocities along the line of sight to the observer, to very high accuracy. This is because all of the output wavelengths or frequencies are expressed as ratios to that of a very precisely controlled laser which controls the instrument. In fact, the accuracies are now at the point, i.e. measuring velocities to a few meters per second. That's sort of the speed you walk at or drive your car at. And yet we're measuring this sort of speed on something that may be many hundreds of light years away. That it is now in principle feasible to detect planetary companions around stars not by seeing the planet directly, but by seeing the wobble it causes in the parent star. The planet Jupiter going around the Sun causes a wobble with a speed of about 10 meters a second. And if one were observing from some other place in the galaxy with appropriate accuracy, you could certainly detect Jupiter going around the Sun on a timescale of 11 years. And if accuracy was improved considerably more, one might detect the other planets, such as the Earth. The main limitation in principle is whether there are other disturbances at the star's surface that cause apparent variations in velocity which may be comparable to the planetary perturbations in the star's orbit. We're just now starting to look into things at this level of accuracy, although such effects don't seem to be important in the first observations. If these effects do not occur, then this technique is very powerful because one is referring the velocity of the star back to a standard on Earth rather than having to measure relative motion or to detect very faint companions around the source. We're at present doing the sort of basic investigation of how big oscillations and other effects are in stellar surfaces, and at the moment the results look encouraging. If this continues to be the case, we would plan to begin a program fairly soon with the FTS to look for planetary companions around appropriate dwarfs and some giants with spectral types similar to that of the Sun. On the basis of binary star work done, much of it here at Kitt Peak, it's clear that binary stars or multiple star systems are the rule rather than the exception in our galaxy. And that gives one great encouragement that planetary systems are similarly common rather than rare. Obviously, finding planetary companions around stars such as the Sun is a next step in, or one next step in the search for extraterrestrial life similar to our own.
The measurement of an actual distance to even one of the stars transformed our vision of the nighttime sky. We learned that the universe was much more vast than we had thought before. And as we grew smaller and more distant from our neighbors, we began to search harder for other solar systems and for the presence of life, perhaps, upon planets which might be found within them. And whether we pondered the simulated stars in this planetarium theater or in the real nighttime sky, we sense within ourselves that urge to know more about the universe in which we live, as well as our desire for company among the stars.